Hello everyone, my name is Mario Tiozzo and I am the Data Analysis and Visualization Librarian here at UNB Libraries. Today we're going to take a look at how to analyze some PISA data series by using regression analysis. We'll look specifically at creating and understanding a regression output in Excel for the same variables that we created our scatter plot in the previous video. As a reminder, those two variables were ESCS. ESCS stands for Economic, Social, and Cultural Status, which was the independent variable, and the math scores, which was the dependent variable. We remember that the equation of the line of best fit for those two variables was 24.807 times the ESCS score plus 557.36, and that it had an R-square value of 0.0573 or 5.7%. Before we jump into it, let's take a minute to examine what is a regression. A regression is simply a statistical method that estimates the relationship between a dependent variable and an independent variable or variables. In our case, we'll be doing linear regression, which basically involves finding the equation of a line that best explains the interplay between two or more variables. In order to do regression analysis in Excel, we need to make a quick modification to it before we get started. We're going to be using the Data Analysis Pack, which is an add-in to the standard Excel. To see if you have it, go to the Data tab, and if you have it, it should be to the right of the ribbon. If you don't have it, simply go to File, Options, Add-ins, Manage Excel Add-ins, press the Go button, and select the Analysis ToolPak and press OK. Now you should see it in the data ribbon. Okay, now that we have our analysis ToolPak, let's start creating our regression output. So to recap, we are interested in seeing if there's any statistical significance between the ESCS variable, the independent variable, and the math score variable, the dependent variable. We could do this by creating a bunch of formulas, but instead let's use our handy dandy data analysis pack to do this more quickly. So let's click on the data analysis button. Let's select the regression option, press OK. Input Y range, which is the dependent variable, so we'll highlight the math scores, including the label. Control Shift down. Input X range, that'll be the independent variable. So we'll select the ESCS variable, including the label. Control Shift down. And because we've included the labels, we'll click on the label box here. We have the output options over here. We can output it in a new worksheet, but let's output it right next to our data so that we can play with it and see the data next to it. So output range, we'll select E1, press OK. Let's move this out of the way. Now we have a regression output table. Let's go over some aspects so that we understand what we are looking at. First, let's right size the column width to get a better view of the data. Highlight it all here. Great. There's a lot of data here, so let's try to hit the main components of the output. Let's start with the regression statistics section. The first data point of note is R-squared. This measures how much of the data or the variation the model explains. In this case, the model is just one variable, the ESCS scores. So how much does the ESCS data explain the variation in the math data? R-squared ranges from 0 to 1, so it's a rate. 0.057 means that the model explains roughly 5.7% of the variation, so not a lot really. Perhaps we should consider adding more variables to this model to increase its explanatory power. Note that increasing the number of variables will increase your R-squared, but if you have more than one variable, you should really be looking to see if your adjusted R-squared is increasing to get a better sense of whether or not your model is truly capturing more relevant data or if you're simply bloating your R-squared. Also note that the R-squared is identical to the R-squared in our scatter plot, which does make sense because it's the same two variables that are being analyzed. The next data point of note in this section is the number of observations. So that's just the total number of rows in this data set, similar to doing a count formula in Excel. So in this case, there are 5,593 observations. Okay, let's move on to the next section of the regression output, the ANOVA table. ANOVA is short for Analysis of Variation. We have three subsections, the regression, the residual, and the total. The total is easy. It's a total of the regression and the residual. You can see that it only has two numeric values, and they are the sum of their respective columns. The regression is the part that addresses our model, so the independent variable or variables. The residual, or sometimes called the error section, is everything that is not explained by the model. Okay, let's go over the columns one by one. DF stands for degrees of freedom. We came across degrees of freedom briefly when we saw the sample variance in a previous video, although we did not call it that at the time. Let's see how it breaks down in this instance. The total number of degrees of freedom is n minus 1, where n is the total number of observations. You can see it here in the sample variance calculation as well. The number of degrees of freedom for the regression section is the number of independent variables in this model. In our case, it's 1. The value is also referred as k. The number of degrees of freedom for the residual is n minus k minus 1. So total degrees of freedom minus a regression degrees of freedom. The next column is SS, or sum of squares. We came across sum of squares again when we calculated sample variances in a previous video. So we know how to calculate the sum of squares, and doing so for the math score will give us our SST, or sum of squares total. Calculating the SSR, or sum of square of the regression, and SSE, the sum of square of the error, or the residual, is a little more convoluted. I won't go over how to do it step by step, but I will show you how to do it for the keeners who want to understand how to recreate this section of the table. So here's a column to calculate SST. As you can see, it's just a classic sum of squares of the math score. This is how we calculate SSR. This is how we calculate SSE. And then you just sum up all the corresponding lines to get your values. And note that the SSR, SSE, and SST calculations match up exactly with the regression output. So the SST explains the variation in the Y data. In our case, the variation in the math scores. The SSR is the portion of the variation in the math score that is explained by our model. And the SSE is the portion of the variation in the math score that is unexplained by the model. So we have the portion that is explained by the model and the total variation. What if we divided the former onto the latter? Let's do that. SSR divided by SST. We get the rate of what is explained by the model. Basically, we get R squared. Okay, let's move on to MS, which stands for mean square. To calculate this, you simply take your SS value and divide it by your degrees of freedom. So we go here, we take the SS value of the regression and we divide it by the degrees of freedom of the regression. This gives us the MSR. Since we only have 1 degree of freedom in our model, our SSR and our MSR will be the same value. Our MSE will change, however. MSE. This calculates how much is each observation or each data point missing our prediction on average. Just tag this. Note that our calculated MSR and MSE match up with our regression table output. Moving on to the F column, this is the F statistic. To calculate this, you take the MSR and divide it by the MSE. Let's take the MSR and divide it by the MSE. The higher the F-stat, the higher the significance. The way to illustrate the F statistic is F, open parenthesis, regression degrees of freedom, comma, residual degrees of freedom. So in our case, it would be F, open the parenthesis, regression degrees of freedom is 1, and residual degrees of freedom is 5,591. Close the parenthesis. Let's tag it. The following column is the F significance. This is essentially the p-value of the F statistic. It will tell you if the model is significant or not based on a predetermined level of significance or alpha, typically 0.05. If the p-value is below that number, it is statistically significant. If it is higher, it is not. You can use a table to get that value, or there's an Excel formula for that called F.DIST.RT. Open the parenthesis. We note that there are 3 arguments, the X, or the F-stat, the degrees of freedom for the regression, and the degrees of freedom for the residual. So the F-stat is right here, degrees of freedom of the regression is right here, and degrees of freedom of the residual is right here. Close the parenthesis. We get a whole bunch of zeros, but if we change the formatting to scientific method, let's increase the decimals here, we get the exact same number as in the summary table output. So in this case, the model is statistically significant as the p-value is well below the 0.05 threshold. Put a tag here. There we go. So the ANOVA table assessed the model as a whole. The next section assesses the individual variables. So we have a row for the intercept and one for the single variable in our model, ESCS. Let's focus mostly on the latter for our purposes. The first numeric column is for the coefficients. So this tells us that the y-intercept is at 557.36 points, which means that the model expects the math score to be 557.36 if all the other variables in our model, in our case only ESCS, are 0. The ESCS coefficient is 24.81, which tells us that for every additional ESCS point a student has, the model predicts that their math score is expected to increase by 24.81 points. We can see that this is a positive relationship between the ESCS and math variables. With these coefficients, we can create an equation of the line of best fit using y equals mx plus b, where the ESCS coefficient is m and the intercept coefficient is b. The equation would look something like this. Note that this equation is identical to the equation on our scatter plot, which makes sense because it's the same two variables that are being analyzed. From that equation, you can make predictions. Given a certain ESCS score, you can predict the math score. Remember that the R-square is not very high for this model, however, so the reliability of the predicted score would be fairly weak. Next is the standard error. We have seen standard error in the past, so I will not spend too much time here except to say that it is a way to determine variation within a data series. The next column is the t-stat. We have seen the t-stat briefly when we discussed confidence intervals. It is calculated here by dividing the coefficient by the standard error. So let's do that. Take the coefficient of the intercept divided by the standard error of the intercept. We get the t-stat of the intercept. Drag this down. Get the t-stat of the ESCS variable. A higher t-stat implies a higher significance and vice versa. Note that this is a two-tailed test. If you wanted to do a one-tailed test, you would need to divide the results in this section of the table by 2. The p-value is the same concept as the one we talked about in the F-test earlier in the ANOVA table section. This is essentially the p-value of the t-statistic. It will tell you if the variable is significant or not based on a predetermined level of significance or alpha, which is typically 0.05. If the p-value is below that number, it is statistically significant. If it is higher, it is not. You can use a table to get that value, or there's an Excel formula for that as well. Let's go down here. So the formula is called t.dist.2t for two-tailed. We know that there are two arguments, the x for the t-stat and the degrees of freedom. In this case, the degrees of freedom for the residual. So we can put our t-stat here for the ESCS score and the degrees of freedom for the residual, which is right here. Close the parenthesis. We get a bunch of zeros again. If we apply the same formatting as we had before for the significance f, let's apply that here. We get the same value as in our summary table output. So let's tag that. In this case, the ESCS variable is significant as it is well below our 0.05 threshold. Note that the p-value for the ESCS variable is the same as the p-value for the entire model. This makes sense in this instance because the ESCS variable is the entire model in this case. The final columns in this section are the confidence intervals. We went over how to calculate this in a previous video, so I won't spend too much time on this other than to say that at a 95% confidence level, we get the lower and upper bounds for our respective coefficients. Importantly, the interval does not include 0, which makes sense. If it did include 0, it would not be significant. So that was quite a bit of digging into this regression output. What can we conclude? We can conclude that the ESCS variable does appear to influence the math score due to the p-value results. Similarly, the model itself appears to be relatively robust given the p-value of the F-statistic. Unfortunately, the R-square value does tell us that the model offers limited explanatory power on the variation of the math scores. Overall, some mixed results, which may require us to reconsider how to go about building a model that is not only statistically significant, but also has more explanatory power in order to, among other things, provide better predictions. Okay, I think that will do it for today. We were able to add the data analysis ToolPak to our Excel, and from there create and go over a regression output table. I hope that this was helpful. Thanks for watching, and I'll see you in the next video. Bye for now.